16 QAM. The objective of the experiment is to simulate the transmitter and receiver for 16 QAM. QAM stands for quadrature amplitude modulation, and to plot the average probability of symbol error as a function of signal to noise ratio EB by N0, where EB is the transmitted energy per bit and N0 by 2 is the double-sided power spectral density of additive white Gaussian noise with zero mean value. So I will start with the theory part. What exactly is quadrature amplitude modulation? Is a combination of amplitude modulation and PSK. So it include the advantage of both amplitude modulation and PSK. In this QAM modulation scheme, signal in which two carriers are shifted in phase by 90 degrees and then modulated and combined. As a result of this 90-degree phase difference, they are in quadrature, and this gives rise to the name quadrature amplitude modulation. The one signal is called in-phase component and the other is known as the quadrature component. The resultant overall signal consists of the combination of both in-phase component and quadrature component. And in view of the fact that both amplitude and phase variation are present, it may also be considered as a mixture of amplitude and phase modulation, as I already discussed. It includes the advantage of both AM and PSK. Now, let me discuss with the constellation diagram of 16 QAM. In the constellation of the 16 QAM, the 4 bits in each constellation point can be considered as 2 bits, each on independent 4 PAM modulation on I-axis and Q-axis. I is in-phase component and Q is quadrature component. So, so if in this diagram, if we look at in this diagram, the 16 QAM constellation has 16 symbols, and there are 4 alphabets representing these 16 symbols: -3, -1, 1, and 3. So in both I axis and Q axis, there are 4 alphabets: -3, -1, +1, +3. These represents 2 bits from 00 to 10. Each of these I phase, I component and Q component represents 2 bits, which supports overall 16 symbols. So in order to simulate this 16 QAM, the transmitter and receiver, and to determine the signal error rate, we write a MATLAB script. So in that MATLAB script, we will first define the variables. So the first variable we are taking is the number of symbols. So in this 16 QAM, we are taking 2 into 10 to the power 5 symbols. So we are defining a variable capital N, which is equals to 2 into 10 to the power 5. That is the total number of symbols in the 16 QAM modulation. The second variable what we are defining is the alpha 16 QAM, which is the alphabets. Now remember, in the constellation, there are 4 alphabets we are using: -3, -1, 1, and 3. So these are representing the alphabets of 16 QAM. Now, if we compare this modulation scheme with the normal QPSK scheme, in QPSK, 2 bits are combined in 1 symbol. So in QPSK, there are only 2 alphabets, 1 and -1. But here in 16 QAM, there are 4 alphabets: -3, -1, 1, and 3. The next variable we define is signal to noise ratio. In dB, signal to noise ratio ES underscore N0 underscore dB is the signal to noise ratio value, and we are taking this value from 0 to 20. So we are taking this signal to noise ratio in decibel unit is from 0 to 20. Now this IP hat is the value or the the output value. We are taking this output value equals initially taking this output value equals to 0. So zeros command is used to define zeros 1 comma n is basically a row vector. So it is a single row and column, and all values are equals to 0. So it is a row vector. So initially IP hat is the output. Initially output digits we are taking all equals to 0. So these are the variables which we have defined in our MATLAB script. So next is signal transmission and detection. How signal is transmitted and how we detect that signals after passing through AWG channel. So initially we are taking a loop, for loop, in which we are taking the length of variable I equals to 1 up to length of signal to noise ratio. Since our signal to noise ratio value in dB is from 0 to 20, so this length will be obviously equals to 20. So this for loop will go from 1 to 20. Since we are plotting the we want to plot the value of signal to noise symbol error rate with respect to signal to noise ratio, and hence both the vectors should be of same length. That's why we are taking this loop in order to determine the symbol error rate. The length of the vector of the symbol error rate should be same as the length of the signal to noise ratio. Now this is our input symbol. We are generating an input symbol with this command IP is equal to rand function. Now a simple rand function, suppose we are writing a code rand 1 comma 2, then it will generate a random sequence between 0 to 1. The number of rows in that sequence equals to 1, and the number of columns in that sequence will be equal to 2. So 1 comma 2, the size of that vector will be equal to 1 comma 2, and it will generate a random sequence between 0 to 1. The difference between a random sequence and rand command and a rand src command is that the rand src command generates a random matrix using a prescribed alphabet. Now in this command there is one more variable is there, alpha 16 QAM. Now this rand function will not generate bits between 0 and 1. It will rather generate according to the values given in this alpha 16 QAM. It will generate between values 0 and -1 to -3, including -3 to +3. Okay, so since our input sequence is a complex number, so there will be a real number as well as imaginary number. So the sum of these two will give us the input sequence. Now what we are doing here is to get the transmitted signal, we are normalizing this input sequence by multiplying this vector. It will normalizes the normalization to get energy equals to 1. This command will generate our noise signal. Again, this 1 upon square root 2 is for normalization. Rand n command will generate a random noise sequence with the row value equal to 1 and column equal to capital N. Again, this is a complex number, so there will be a real part and imaginary part. Generate a wide Gaussian noise with variance equals to 0 dB. Next is the received signal. Since we are considering the channel to be additive wide Gaussian noise channel, hence the signal S will be added to the noise signal, and since we are not since we have to get the value of exact value of noise signal, this n will be multiplied by the signal to noise ratio value without dB value of the signal to noise ratio. So this value is without dB value of signal to noise ratio multiplied by n will give us the value of noise signal. It will be added to the transmitted signal S. So the y will be equal to transmitted signal S plus the noise signal. So this will be the output of our transmitter. At the receiver, what we are getting is uh, we are separating the real and imaginary part. So y underscore re is the real part, real component of the y, which we have transmitted, and y underscore im is the imaginary part of the symbol we have transmitted. So these are the two symbols. Now, in order to get the output symbols, we have three alphabets: -3, 3, -1, and 1. So what we are doing here is first we are determining the real part of the output. So IP head underscore RE is the real part. So for three alphabets, we are calculating the values of IP head underscore RE. What we are doing here is now in the first case, what we are doing is we are comparing this y underscore RE value with this factor -2 square root. Again, this is the normalized value. So what we are doing precisely is we are getting the values of real part of output, which is less than -2, and we are comparing with the value equals to -3. So we are finding out the values, and this will give us the value of against this alphabet -3. Similarly, we are calculating the values for alphabet 3, -1, and 1. And similar calculation is we are doing for the imaginary part also. So the total output value will be equal to the real part and imaginary part. And the error will be equal to the input value minus the output value. And we are finding the difference between these two values, and the total size will give us the error. So after the error calculation, we will calculate the symbol error rate, which is the total bits in error divided by total bits transmitted. Now the theoretical value of the bit error rate or symbol error rate or the 16 QAM is the 3/2 error function square root EB by n naught. So this EB by n naught value is without dB value, which we have defined initially. So in order to plot this, we will use semi-log graph, semi-log y, signal to noise ratio in dB. First, we will plot the theoretical bit error rate, and then we will plot the simulated bit error rate. So these are some extra commands to separate the theory and simulation graph, labeling of the graph, and the title of the graph. So this is how the result will look like. The blue color is the theoretical bit error rate, and the magenta color is showing this simulated signal error rate. So let me show you the simulation in the MATLAB. So this is the MATLAB window. And this the program is already written in the editor. So let me run this program and show you the result. So this is the workspace, and there are various variables in this workspace. The alpha 16 QAM, there are alphabets, 4 alphabets, EB by n naught, as the signal to noise ratio dB values. So let me share the result. Uh, so this is how the output looks like. Again, this is blue color is showing the theoretical signal error rate, and the magenta color is showing the simulated signal error rate. There is a slight difference between these two. And as the signal to noise ratio increases, the symbol error rate decreases, because as the signal to noise ratio increasing, that means either noise power is decreasing or the signal power is increasing. If noise power is increasing, that means there are less chances of error, hence the signal error rate will decrease. So that's it for this video lecture. Thank you.